Hello all, good morning. This is Dr. S. Subbalakshmi, an Assistant Professor in the Department of Mathematics, SNS College of Technology. This is a lecture video series on the course Multiple Integrals, and now we are on to the topic of case study on multiple integrals. First of all, we will look on to the context and purpose of this study. This case presents two independent applied problems using multiple integrals. So in this case study, we have got two application oriented problems. Computing the volume of a solid bounded by, we are going to compute the volume of a solid bounded by a paraboloid and a plane. And the second one is we are going to find the probability over a triangular region for the given PDF. These are the two problems we are going to encounter. Each problem is given with a short real-world motivation, a precise mathematical statement, a step-by-step solution, interpretation of results, checks and brief extension ideas that you can use in classrooms or the assessments we have been given. Now, moving on to the volume of a parabola, the very first problem. The motivation behind the problem encountering is estimating storage volume of a basin or an open tank whose top surface is shaped by a paraboloid is a routine engineering task. Wherever we look on to the paraboloid shape, we will have a task regarding this volume. For example, in the great reservoirs or in cooling ponds, we will be having that particular task. So the accurate volume calculation informs material estimates, capacity planning and safety margins. These are the things we are going to undergo after building up the tank. So we are in need of volume calculation. First of all, the problem statement is we are going to find the volume of a solid bounded by z is equal to 4 minus x squared minus y squared, which is a paraboloid, and by the plane z is equal to 0. We can notice that this z is equal to 4 minus x squared minus y squared is a paraboloid and z is equal to 0 is the plane. Now moving on to the solution of the given problem. We are going to identify the projection D in the xy plane where z is greater than or equal to 0, that is 4 minus x square. That is 4 minus x square minus y square is greater than or equal to 0, which means what we infer from this, it is x square plus y square is less than or equal to 4. So D is the disk of radius 2 centered at the origin. We can notice from the equation that D is a disk of radius 2 centered at the origin, and we can express this volume over the double integral d 4 minus x squared minus y squared into dA. Now moving on to the next solution properties. Switching to polar coordinates. Why we are switching on to polar coordinates? Since we cannot deal with variable integration, we are moving on to polar coordinates. X is equal to r cos theta, y is equal to r sin theta, as usually we have taken. Now dA is equal to r into dr d theta. Then the integrand 4 minus x square minus y square is equal to 4 minus r square. We can notice that the brackets inside this thing will be changed to 4 minus r square, and the limits r will be from 0 to 2, when theta will be sub 0 to 2 pi. So now setting up the integral, volume V is equal to double integral 4 minus r square minus into r into dr d theta, and we are just calculating as usually. We will be getting at r is equal to 2, when the radius of disk r is equal to 2, we will be having the values like this, which means on mere simplification we will have the volume of the paraboloid under the plane as it is equal to 0 is 8 pi. So what we have done here, we have just taken this paraboloid and the plane, we have just calculated it with the volume. Later we have used polar coordinates and we have simplified the problem when r is equal to 2. Now we have got V is equal to 8 pi cubic units. This is what our volume shows. Now moving on to the second problem. The second problem is probability over a triangular region, which will be considered as a statistics or probability application. So now the motivation behind this is joint probability density functions defined on a region arise in modeling correlated continuous variables, which means this arises when we are correlating two continuous variables. Calculating probabilities over subregions. Subregions is very difficult task. It's a frequent task in reliability, signal processing and spatial statistics. These are the subjects wherein we will be using this multiple integral problem in implementing in probability problems. This is the motivation behind choosing this problem. Now, what is our problem statement? The problem statement is we are going to have a probability density function here, join probability density function here over, it is a unit square of 0, 1 into 0, 1, and we will have the function to be k into x plus y. We have to determine k and probability of x plus y less than or equal to 1. Now moving on to the solution. We are going to find the normalizing condition. Double integral over k x plus y into dx dy is equal to 1. Which means this is our integrand k into x plus y into dx dy, which is our integrand here, and we are double integrating it, and we also knew that it lies in the limit 0, 1, which is a unit square. We are just implementing all the limits. The limits have been implemented here, which is 0 to 1 and 0 to 1 for both of the variables x and y. Just a mere simplification as we have done in the previous classes, we have done it, and at k is equal to 1, we notice that f of x plus y is equal to 1. Therefore, this inner integral becomes as a solution. Now we have to compute probability of x plus y less than or equal to 1. The event x plus y less than or equal to 1 corresponds to the triangular region. We also knew that it corresponds to the triangular region T, and which is fitting inside the unit square. These are all the set builder notation of the given problem. Now what we can notice at is, we can notice that we are setting up the integral here, probability of x plus y less than or equal to 1, which is nothing but double integral over t x plus y into dx dy. Just implementing the limits. X plus y into dx dy, and on mere substitution and simplifying the problem, you will have the answer. So simplify it stepwise and we will have the answer to be 1 by 3 when the probability of x plus y less than or equal to 1 is 1 by 3. So this is how we case study a problem related to multiple integrals. Now we have seen both the problems related to an engineering task and a probability task. Likewise, we will case study the subject multiple integrals. We will look on to the other concepts in the next video. Thank you.